last time or the last few lectures we have been discussing temporal coherence in some detail. So today we will try to work out a simple example on temporal coherence and then try to move on to spatial coherence. So, right. So let us consider the Young's double slit setup. So the width of the separation between the slits is 2D, and then the field from the source passes through the two slits. Now this is the z-axis, and let us say we want to measure the field at this point. So this is z equals 0, and this is z equals r. So the screen is at a distance r from the slits. So let us say that from slit 1, the field takes a time t1 to reach the point of detection. Likewise, from slit 2, the field takes a time t2. So let us, for simplicity, consider a spatially coherent constant amplitude plane wave field. So which means the intensity is constant. Furthermore, the field is temporally stationary. So we are invoking the ideas that we have been discussing over the past few weeks. With a spectral density given by a Gaussian form. This is something that we considered last time. With omega naught much larger than delta omega. So this is the quasi monochromatic approximation. And the separation, of course, let us also assume that r is very much larger than the separation between the slits. These are the standard assumptions we make. And the size of the two slits is negligible. Now the question we wish to address is the following: how we could find the frequency bandwidth delta omega of the field by measuring the intensity I of x on the screen as a function of x. So basically this is x. Okay, so this is the origin, and basically x is the point from this reference point. So the question that we wish to address is, how can we find frequency bandwidth measuring on the screen So basically, if we measure the interference intensity of this of the field at this point, so basically if we can measure the intensity or the visibility of this interference pattern, from that information can we find the frequency bandwidth of the spectrum of the source? So that's the question that we wish to answer. So okay, so the question that we wish to address is the following. So this is the setup. We have the Young's double slit setup, we have the field, and we have two slits. The separation between the slits is 2D, and the screen is placed at a distance r from the slits. Now of course r is very much larger than the separation between the slits. Now if we measure the intensity of the field from both the slits, say at a point x, the question is, by measuring the intensity at this point, let us call this point P, can we determine the frequency bandwidth of the field? So basically, from the interference information, by measuring the interference pattern, can we determine the bandwidth of the source? So that's the question we wish to address. Okay, and we have been told that the field is stationary, and this is the spectral density. Okay, and we had to determine delta omega, right? So once again, we know that the field at this point P can be written as V1 of d t minus t1 plus k2 v of minus d t minus t2, correct? Because let us say this is the origin, so the coordinate of this point will be d, and the coordinate of this one will be minus d, correct? So v of d, this one v of v1 and v2, we can just add a subscript. So v1 of dt minus t1 and v2 of minus dt minus t2 are the field amplitudes at the z equals 0 plane at these 2 points respectively, at these 2 space-time points respectively. Now k1 and k2 are constants. Now the intensity on the screen is given by this formula. This is the well-known formula. So in which case we'll get k plus its complex conjugate. So maybe once again I'll write down the expression somewhere here.
In this context, how do you figure out this K1 and K2?
So K1 and K2 are basically, typically they are complex numbers that would be due to the difference in the path length, the phase shift, so on and so forth.
It will correspond to some phase.
Some phases basically. Yeah. But in this case, since we have assumed that it's a constant amplitude field, the intensities will be constant. So let me just write down the expression for intensity once again, because there is no space on that side. So this is what we get when we formally put v of xt and its complex conjugate and expand the term. Now this is nothing but mod k1 square. The first one is the intensity, the first term at the location d and time t minus t1. The second term is again, it corresponds to the intensity at minus d measured at t minus t2. And the third and the fourth terms are basically they correspond to the cross correlation function. So this will be the complex conjugate of the other one. Okay. So now, so since you are considering a constant amplitude plane wave field, the amplitude of the incoming field, that is the field at z equals 0, is independent of the spatial location. So which means we can simplify this further and simply write, we can drop the spatial coordinate because the intensity is constant. Right, that's what it is. So we are dropping all the spatial coordinates and just writing down, including the time coordinates, because we are dealing with temporal coherence, so we are not interested in the spatial part. So we know that the field is temporally stationary. That's given to us. That's an assumption that we have made. So since the field is temporally stationary, so this holds. Since the field is stationary temporarily, the cross correlation function will only depend on the difference between T1 and T2, right? So it's tau that matters, and gamma of tau is related to the spectral density this way. So they form a Fourier transform pair, and this is the Wiener-Khinchin theorem, right? So we know what S of omega is. That's given to us. So we just plug that one in. So if we integrate it out, we will get integrate over omega. So this is what we will have. Okay. So tau is T2 minus T1. But the question is, we don't know what tau is. Our goal is to determine delta omega. So this is the quantity that we want to determine. Okay. So delta omega is what we want to determine. But for that, we need to know what tau is. When I say we need to know what tau is, what is tau in terms of all these parameters, d, r, so on and so forth. So what do we do? Let us look at the schematic. So T2, take T2. So T2 is given by right, because this is x and this distance is d. So T2 is so basically the length which is given by c times T2 is given by r square plus this distance from the theorem of Pythagoras. Okay, so we are going to divide that. We are going to divide both sides by c because we are only interested in determining T2, right? So which means this is r over c times 1 plus x plus d by r by half. Now, since r is much larger than x and it's much larger than d, what we do is we are just going to make a binomial expansion and just retain the term up to first order. So this is what we have. So which means it's 1 by c times r plus this is what we get. So likewise, T1 is nothing but 1 by c times r square plus x minus d the whole square raised to the power half, because this is T1. So this distance is x minus d, right? So once again, we can make a similar binomial approximation, binomial expansion, and truncate it to first order. So this is what we get. So now what is tau? T2 minus T1, which is nothing but this term. So So this is what we get. Okay, so now we have this information. So we know what the time difference, what the delay is in terms of x, d, r, and c, in terms of all the parameters in the setup. Now, once again, let us write this one down explicitly.
You are assuming it is a wave.
Yes, so this is a plane wave. So we are assuming it's a plane wave. So pretty much many, even in research problems, we always assume the field to be a plane wave.
Yeah, no, that is true. And plane wave, of course, is very, is very ideal.
That is true. That is true. That is true.
Because if you have some straight,
oh yes,
like if you have the beam has been waste, then of course you cannot have this kind of relationship.
yes. So
You cannot apply this Pythagoras theorem there.
that is true. Very true. So whenever we deal with beam, when we consider a real beam, over there we have to take into account the spatial coordinates, in which case the notion of spatial coherence coherence comes into play, but that's what we'll be doing next, discussing next. But even there, for many problems we make the paraxial approximation.
Yes.
So where we assume that the effect of diffraction is negligible, the spreading is minimum.
I mean, this is basically, kind of plane wave.
Yes. So once again, even over there we try to simplify the problem by making the paraxial approximation. So the intensity, once again we are just writing down the general formula for intensity in Young's double slit setup, because we just want to put in the value of tau explicitly. So and then so this is the standard thing. So once again, let us just write here what was gamma of tau that we calculated. So the intensities are constant, they don't have any time dependence, so we'll just set them to be 1, we don't lose anything. So now we are simply left with now phi gamma is basically the argument of gamma of tau, which is nothing but omega naught t, right? So we are almost there. So this is what we will measure. So this is the expression for intensity as a function of x. So the question is, there is no x here in this expression, but that x comes through tau, because tau is related to x. So all we have to do is to substitute for tau explicitly in terms of x, d, and r. So here you see that we see that the intensity does vary in a sinusoidal manner, because that is the due to interference. So let me just go over so the point once again. So this is a general expression for the intensity. Now the intensities are constant. I mean, this is the general expression for intensity measured at a point x on the Young's double slit setup. Now we have been told that we have the field has a constant amplitude. So I naught of t at t1 and I sub 0 at t minus t2, they are constant, so we just take them to be 1, we don't lose anything. And now this is what is the expression for intensity in an interference experiment. So the question is, we need to explicitly substitute for mod gamma of tau and phi gamma. So we calculated gamma of tau, and the phase is basically given by omega naught tau. That's what we write here. And then mod gamma of tau is given by this Gaussian. That's what we put here. Now the question is still, we don't have any x dependence on the right hand side, and that comes by writing down the expression for tau explicitly in terms of x. So when we put that one here, this is what we get. Now you see that the intensity does vary in a sinusoidal manner because we have this cos term here. However, the visibility of these interference fringes will decrease as a function of x because of this Gaussian here. Now we know that the visibility essentially depends on the degree of coherence, that is gamma of tau, right? Now visibility depends on gamma of tau. So So the standard deviation of this envelope is given by right. So by basically measuring the standard deviation of this envelope, you can determine what delta omega is. We can find out the bandwidth of the spectrum. Okay, so that's how we determine the bandwidth of the spectrum by measuring from by performing the intensity measurement. Right. So first we measure the intensity as a function of x on this setup, on Young's double slit setup, and then we know how the visibility decreases because we know the exact form of the spectrum of the optical field. So the degree of visibility essentially depends on the degree of coherence. So we know how the coherence is related to x, d, r, and delta omega. So we simply measure the standard deviation of the envelope, okay, and that is related to delta omega. So from that one we can determine what delta omega is. So this is how we do it. So this is a simple example to illustrate how we can measure various parameters of the optical field by carrying out an intensity measurement in an interference experiment. Okay, so this pretty much wraps up our discussion on temporal coherence. So now we will move on to spatial second order coherence. So the question that we wish to answer here is the following. So what is the correlation between fields at points So please note that rho is the transverse spatial coordinates x, y. Okay. Now typically R, the three-dimensional position vector, is given by these three coordinates x, y, and z. This is rho. So we write down R as vector rho and z. So whenever we talk about spatial coherence, we are only interested in the coherence in the transverse plane. Okay. So we assume that the field propagates along the z direction. So we are not interested in the coherence along the direction of propagation. We are only interested in how the fields are correlated spatially in the transverse plane, in the plane perpendicular to the direction of propagation. Right. So that's why we have explicitly written down R as R1 as rho 1 times z and R2 as rho 2 times z. Okay. So let us recall that the field V of RT can be expressed in terms of its Fourier transform, in terms of its spectrum, right? So this, we'll write the same thing as so once again, since we are only interested in spatial coherence, we have dropped the label omega because we are not interested in that one. We are interested in just how the field is correlated at different points in space. Okay. So what this means is U of RC is the field at point R So it is not as if the field does not depend on omega. We are just dropping that label because we don't want to write down too many labels that we won't be using. We are not interested in temporal coherence anymore, so we are not interested in explicitly writing down the frequency in the argument. We are only interested right now in in spatial coherence. So that's why we are simply writing the field in terms of rho and z, the transverse spatial variables, and z, the direction of propagation. Let us see, you have the field. So this is basically this is the observation point. So this is the z equals 0 plane. Now So let me yeah, I can erase this part here. So the total field is given by z is 0 because we are assuming that at the source corresponds to z equals 0 plane. So z is 0 at the source. Okay. That's why here we have put 0 at both the places. Okay. So this is total field at the point of observation. So once again, if you have to recalculate the intensity, plus the complex conjugate of this one. So this is the total intensity at the point of observation. So of course, similar to what we did in the previous case, that is for temporal coherence. So what I was saying was that the total intensity at the point of observation is basically a sum of the intensities of the fields at these two points, and the fields passing through these two slits. So we simply write down the total field, and then the intensity can be calculated this way. This is the standard formula for intensity. And once again, by looking at the intensity at the point of detection, we can obtain the information about the spatial correlation between the fields at the source point. Okay, basically at z equals 0 plane. Now, how do we go about doing this? Basically, what is it that we wish to do? So the goal will be to calculate quantities similar to what we did in the case of temporal coherence. So what I was saying was that by looking at the intensity at the point of detection, we can obtain information about the spatial correlation between the fields at the source plane. Right. So now the question is, when we study spatial coherence, there is an important quantity that we need to introduce, that's called the angular spectrum. So this is something that will show up at many places, both in classical and quantum optics. So when we move on to quantum optics, when we study the production of entangled photons through spontaneous parametric down conversion, the notion of angular spectrum will once again show up naturally. So yeah. So beam-like. So this is something that we will introduce here. So the fields are basically beams. So the underlying physics doesn't change whether we consider the propagation of the field in the positive z direction or the negative z direction. So, but in our analysis, we'll just consider the field propagating in the positive z direction. Okay. So once again, let us recall. Yeah. Yes.
What do you mean by beam here actually?
Oh, so it's like you take a laser source, you turn on the pump, right? So what comes out is not a simple wave, it's a beam. So beam is something like this, which will have a finite wave size. So it's not a simple it's not a simple plane wave. So
Okay.
so beam is what you see in the lab.
Okay.
So this is so just like a time varying signal has a Fourier representation in the frequency domain, a space varying signal also has a Fourier representation. It's in the spatial frequency domain. So we'll assume that u of rho z so this d square q is basically dqx dqy, right? Or if you want to write explicitly in terms of x, y, and z, so so please note that we are only considering the two-dimensional Fourier transform. xy, rho x, rho y, qx, qy. Okay. So we are only interested in what happens in the transverse plane, that is plane perpendicular to the direction of propagation. So we are not going to consider any kind of correlation along the direction of propagation. Right. Now the field V of RT satisfies Maxwell's with the wave equation. This is well known because any optical field will satisfy the wave equation, right? Now u of rho z, this part satisfies what is known as the Helmholtz equation. Now, why is this the case? Because we assume that the optical field V of RT can be written as at plus or minus I omega t. So, in a sense, we assume that the spatial part and the temporal part can be separated. So, when you put that one into Maxwell's equation, when this one goes here, we get because this is just derivative with respect to the spatial coordinates. So, this is k square, omega over c is k, right. So, and this goes away. Yes, so yes, we will enforce the partial approximation later, but right now the first assumption that we are making is the optical field can be written down, the solution to Maxwell's wave equation can be written down as the product of the spatial part times the temporal part. So, so basically the field is separable in space and time. So, that is the assumption that we make, the first assumption we make. So, under that assumption we get the Helmholtz equation. So, basically so this is k vector so this is qy, qx, and this is kz, or sometimes in literature it's also denoted as w. Okay. So, omega is ck, we assume a linear dispersion because that is what we have in free space. K is qx, qy, w, or kz, or it can be written as, and the length of the transverse wave vector qy square. So, so let us write this down explicitly. D squared by dy squared zero. Now, we know what u of rho z is in terms of the Fourier components, right. So, we are just going to so we just substitute the explicit form for u of rho z in terms of its spectrum in the Helmholtz equation. So, when we do that, we get there is no z dependence here on the exponent. So basically but when you take the derivative with respect to x and y, you get minus qx squared and minus qy squared. Now we can combine k squared, qx squared and qy squared. So that will give us so this one we call it w square or it's kz square, but typically we will stick to w because that's pretty much is used in the literature. So this is important. So then we are left with so please note that this w, if you take the square root, right, is positive because when you take a square root it can have two solutions, a positive and a negative part. The positive solution corresponds to the propagating field. Either you call it the propagating wave solution or the propagating field solution, doesn't matter. And this is if so this is the decaying wave, or what is more technically known as the evanescent wave solution. Now in our discussion we won't be concerned about this part, the second part, the evanescent field. We will only be concerned about the propagating field, but it doesn't mean that this has no relevance. In fact, the evanescent field is relevant, and there's a whole branch of optics called the near field optics that concerns with studying these evanescent fields. So the problem is these evanescent fields are decaying solutions. So they pretty much, the evanescent field decays within the wavelength of the source. So it's extremely hard to detect them. Okay. So in our discussion we won't be concerned about this part. So we'll only be concerned about this part, the propagating part. So yeah. So we have this equation here. Yeah, so this is the one we are interested in. So the generic solution to this differential equation is so this is the most general solution to this differential equation. Okay, once again, let us once again emphasize that we are only interested in the propagating wave solution, the propagating field. So, oh no, sorry. Oh no, oh yeah, I'm sorry. Here we know what your all we have done is simply put the form for u tilde of qx qyz into this expression, what we started with. So e power I w z minus omega t. So this corresponds to the field positive z direction. So this one corresponds to the field in the negative z direction. So we are only interested in the field traveling, propagating in the positive z direction, because the physics doesn't change between positive and the negative z directions. Right. So which means so please note that since you're only interested in the field traveling in the positive z direction, we just ignored the second part. Okay. Now, the important thing, this is not a Fourier relationship, because on the left hand side you have x, y and z, whereas on the right hand side you just integrate over qx and qy. You are not integrating over kz, right? So this is not a Fourier relationship in general. However, at z equals 0, if the source plane is at z equals 0, then now this is a Fourier transform. At z equals 0, A of qx qy is the Fourier transform of u of xy, only at z equals 0, okay? Or other, so which means A of qx qy can be written as these two form a Fourier transform pair. Now, we'll just stop in a couple of minutes. The rest will continue on Friday, but one important point that I wish to make is this A of qx qy is called the angular spectrum representation of the field propagating in the positive z direction. So please note that A of qx qy, the angular spectrum, does not depend on z, right? So once we know A of qx qy, we can then calculate the field for arbitrary z, because we have a direct relationship between u at x, y, z and the angular spectrum, okay? And the angular spectrum is pretty much determined by the source. So when you do an experiment, we pretty much know, we can model the source, we know what its angular spectrum is, okay? So that's how we calculate the field. We write down the field in terms of its spatial variables, okay? So now next time on Friday, what we'll do is we will now try to go further and then try to calculate the expressions for the correlation functions in spatial variables in terms of the angular spectrum. So we'll write down the cross spectral density function, then the correlation function in terms of its angular spectrum, which is called the angular correlation function, so on and so forth. So that's what we'll do on Friday. And then once we are done with this discussion on spatial coherence, then we will move on to quantum optics. Start discussing quantum theory of correlations, what they mean, then discuss Hansberry-Brown-Twiss experiment, Hongo-Mandel, so on and so forth. Okay, and then start our discussion on various quantum states of light. There is one part on optical coherence that we will skip this time. That is called, we can also extend this discussion to angular correlations. and we can also discuss the concept of polarization of light in terms of correlation functions. Okay, but we won't have time to discuss those two. So hopefully next semester, when we try to discuss structured light, we will start with a discussion on angular correlations and then proceed further. But this time we will stop our discussion with the spatial coherence and then move on to quantum optics. So we won't be able to discuss the propagation of optical coherence. So maybe at a later date we will try to discuss those ideas. So any questions?